Ahoy! Today we'll be diving into Bayesian Analysis, Module 3, Deep Dive. I'm Mark Williamson for DaCCoTA at UND. So last time in Module 2 we covered some kind of surface details about the computational process of Bayesian analysis and looked at simple examples in various programs. Today we'll look at more details under the hood when it comes to computation. And we'll look at more detailed examples in R and SAS. Let's do some review before we get too crazy with things. So we've been talking about Bayes' theorem these last two modules and into this one. Again, a concise explanation of it is that updates probabilities or our degrees of belief about some sort of state in the world, like typically some sort of data, after attaining new data. So the Bayes' theorem can be postulated like this. Another way of mentioning it is the probability of A occurring given that B has occurred is equal to the probability that they have both occurred relative to the probability that B has occurred. So you can fill in hypothesis and data with A and B respectively. And when you do so, you get this here. And again, here is a visualization. You're going to take in data and your prior understanding of the situation and likelihood to churn it out with Bayes' theorem to get your posterior distribution, to get an estimation of where your true value or parameter lies. Continuing on here, we've shown this concept illustration last time of what kind of goes into it, but let's dig into a little bit more. So the things we'll need for analysis, we'll need models, priors, data, and how I would say this, both for your model and to a certain extent your priors will need parameters, that is setting certain values for certain things, mostly distributions. Now, steps for analysis. And this is JAG specific, a methodology in R, how you would go about doing this. So first of all, you need to define things. So your model and your prior. So that'd be this kind of step here. You would compile. So you take your data, model, and priors, come in here, and then you simulate the posterior out here. And now some details on the posterior simulation, and we'll go into much more detail, but you can tweak how you simulate your posterior, doing with things like burn-in, iterations, thinning chain number, to get a better estimate of your posterior, more robust and reliable. And we'll go through what all that means. And then you can, of course, examine how well your posterior simulation worked. You can look at your trace plots or correlation leg plots, and then of course the big thing is your probability density functions, which will kind of give you estimates and uncertainty for the parameters you're interested in. Let's keep swimming around the kiddie pool of the basics, make sure we got everything before we tackle the waves. So another way of visualizing this is through this resource here. You have your prior information, your priors, your parameters, you set that in here, you have your model, and then your data, and plugging it through you can get an estimation for how likely that data was. And if you continually iterate through, you can get a good understanding of your posterior distribution. And more broadly, essentially you have parameters that you plug into a model and work on data with, and you just do this over and over again, and that is Bayesian inference. So that's one way of looking at it. Next, let's cut our teeth into the details. First, we're going to talk about how we define a prior. So a prior is a summary of what we know about the situation. Say we're trying to look at the success rate of a certain exam. So where we get the information about the prior might come from expertise in the field. Maybe you're an exam creator, or past experiments or observations. Maybe you've taken an exam before. And this prior can be very precise or very vague. So you can imagine a continuum here, where this is vague, this is precise. You might have something very vague where it's sort of a flat thing. It could be equally probable everywhere, or it could be very precise where it's a very narrow range of what's probable. And you may, be anywhere along that continuum. And so fundamentally, a prior is a probability distribution for a variable or parameter. It tells you across all the range of values how likely each value is. So how do we get it? Well, this is a simple kind of 4 steps to get you in the right direction, especially coming from sort of no prior background of working with priors. First of all, I would say conceptualize it. Think about its mean, its spread, maybe some of its limits. Draw it. And then determine distribution and parameters, so how you'd set it up formally, and then formally model it in a software package. So for example, with our example, maybe you want to get started here. You say, hey, conceptualize it. I think it's maybe going to have about a 50% success rate. That's given my understanding. I've taken it before. I failed it, but my friend passed it, or something like that. And spread, well, it's probably not going to have a 0% and not probably 100%. So it's going to be, somewhere. Let's just say like maybe 20% to 80%. Who knows? And the limits, like I said here, it's probably not any more than that. Draw it. So maybe what it would look like if we think it's around 50%, 0.05. And we think it might be pretty symmetrical, so maybe it'll be something like this, where it's most likely in the 50% and it'll taper off in some way. And then maybe we want to determine distribution and parameters. So distribution-wise, this might be good for a beta distribution because those goes from 0 to 1, but not really including 0 or 1, so this might be a great for us. And some of the parameters, so beta distribution has 2 shape parameters. I'm not going to go into like what makes them, but we want them symmetric, so maybe let's try 4 and 4. And then modeling that in a software package is going to give us this. So these are our shape parameters, and this is about what we like. This looks pretty good here. 50% is the most likely, and it tapers off to like really no probability at 0 and 1. So great. So now let's talk about the effects of priors and data on posterior, because those are the 2 pieces. Priors and data will determine our posterior. So there's a lot of different ways this could be set up. Let's just get started with our priors. So let's just draw some graphs here. Just this hopefully exercise helps you kind of get more familiar with what's going into these models and what will come out. So say a vague prior, we don't really have any information, so we put it across here. Another vague prior, a strong prior, so say have pretty good information. Another strong prior, and then a third strong prior. But then our data here, we might have very vague data, so not very informative data. Strong data, again, pretty vague data. Strong data as well, but then divergently strong data. How does this affect the posterior? Well, vague prior and vague data will give a pretty vague posterior. Maybe something like that. Vague prior and strong data, so that's going to be mostly driven by the data. However, if you have a strong prior and vague data, the prior is going to drive more of the posterior. Strong prior and strong data will have a very nice posterior. Now, if these are very divergent, of course, that's going to have a strong effect where it's going to kind of sort of middle out here. And in this case especially, you would want to get more data and keep working on it to be able to figure out a better distribution for your parameter, like get more information about what it truly is going on. And so you can see here, depending on how your priors and data set up, it can really affect the outcome. Ideally, you have strong prior and strong data that work together, but that's not always the case. Okay. So let's look at some prior distribution examples. I've just sort of waved my hands about it. So let's look at common distributions that are used. So first of all, there's a uniform. So this would be across all values that any value of x down here is equally likely from 0 to 1. Now, how this would be set up, you have your uniform and then min 0, max 1. However, you could have a uniform distribution across a range of values where you know that there's a strict cutoff, like you can't have lower than 25 or above 75, and the distribution would look like this. You can see that it sort of has strict edges. Now, another very common distribution is the normal distribution. So for this example, I have what I call like a standard prior. It's going to be dominated by or described by its mean and standard deviation. And so this is 0 and 1, that's pretty standard. Normal distributions are symmetrical, so it'll be pretty normal. But say we have a very strong prior, so not a lot of deviation, it's going to be a much sharper peak. However, if we have a much sort of weaker prior, like more deviation, it's going to be a lot flatter. But you can see here, since these all had the same means, they're going to be around the same thing, but how certain we are that it's close to 0 depends on how strong that prior is. Now, on the other hand, we're also shown beta, and this is a very flexible one. It can be both symmetric and asymmetric. For example, here, if we have a shape parameter 2 and 5, you can see that's asymmetrical, that this right side here trails off a lot more. We could have beta distribution 2, electric boogaloo, in which we actually have this U-shaped. We could continue on with the franchise. Beta distribution 3, distribution harder. We can have, in fact, what almost looks like an exponential distribution. It's essentially impossible down at 0, but it's very, very likely at 1, and it trails off pretty sharply. And if we round out this series, beta distribution 4, this time it's personal. We can replicate a pretty smooth, symmetrical, not quite normal because it doesn't taper off, but we can see it bounce around 0.5. Okay, now that we've covered those priors, let's look at the likelihood model. So this is also known as a generative model. I gave in that example. They're essentially synonymous. It's a function defined by parameters and priors, or that prior probability. The model will run using the data and define parameters and priors, and really how you set up your model depends on what you are doing. So a very simple sort of, you think of models, you can think of functions, you can think of equations. So a very common equation is y equals mx plus p, where m is the slope and then b is the intercept. What a likelihood model looks like is more like this, where you have y is a normally distributed with mu as our mean and variance as 2, but it's actually not quite that simple. Mu is actually a function as well, and it's going to be a function of b0, b1, bx, and then b0 and b1 might also be functions themselves. So likelihood models are sort of functions within functions that help model our data, etc. And so here are some common ones here and what goes all into them. So there's the beta binomial. Models x as a function of the binomial, n the number, and then p the probability, where probability is in itself a beta distribution with a and b as our shape parameters. Normal, y for each iteration is a normal distributed with mean and standard deviation. The mean is itself drawn from a normal distribution with a mean and standard deviation. And then our S here in this circumstance is a uniform distribution from min to max. Regression, similar to normal here, but then M is actually this sort of equation we kind of looks very familiar to here, A plus B plus XI, and then A, B, and S all come from have distributions. Multivariate could be similar. It's building on this regression. You might have a C as well, and then the ZI. So these come from the X, the Y, and the Z, they come from our data, but then A, B, and C, and S come from modeling these with distributions. Poisson is going to be pretty similar, though it's log transformed, and again, so it's A, B, and C. We'll look at some of these up close and in the flesh when we're doing examples here. So after that, we have compiling and simulating. There's not too much to say here. Model is sort of in the actual the computation. The model is passed and it's compiled. It includes those likelihood and priors. And then a simulation will produce our posterior probability density function with diagnostic information. So a big part of that, what's going on here with the simulation, is this Mcmc you've probably seen several times here, and I've sort of waved my hands and boogied away instead of defining it. Now here, let's define it some more. It stands for Markov Chain Monte Carlo. So Markov chains are random walks where each step depends on the previous step. So the example here is, say you have these parameters, and you essentially randomly walk back and forth, and because it's random, wherever the actual true sort of like most likely parameter of this data will kind of build up the most, and the least likely ones, the ones that take the farthest walks away, will be less likely. And these are really good for essentially exploring space where you can't calculate everything, but you want to calculate enough stuff to be reasonably sure you've captured the sort of the true probability. Again, yeah, explore spaces that can't be fully computed. That's why for a lot of these more complicated examples, computational methods didn't exist to actually run them, so that really hampered Bayesian analysis from doing anything more than pretty simple examples. So this is a lot of times what you'll get with these output of Monte Carlo chains, Markov chains of Monte Carlo, or Monte Carlo and Markov chains, wherever you want to call it. You'll have these trace plots which sort of show the outcome of these random walks, and then your actual probability density function. So some more about simulating. You can do a lot to set these Mcmc simulation parameters. The first is burn-in. That's at the beginning of this random walk. It's often pretty messy and doesn't really work very well. So a lot of times you cut out the first 100,000 whatever samples and only take the later ones, which get better at estimating that probability. You can set up the number of iterations. The longer you run the iterations, the more likely you are to be able to converge on a stable estimation. However, the longer the chains run, the more computational power and longer it takes, so it's often a trade-off. You can also vary the number of chains. You can have multiple chains running at once, and ideally the chain should sort of converge on the same outcome. So here are some examples of 3 chains. This first chain, it looks pretty good. So it's sort of converging pretty well. That it's ending up being pretty flat. That's pretty reliable. Chain 2, we see this long burn-in problem that it is really off here and that before it goes here. And this one, chain 3, there's a lot of correlation, so it sort of goes up and down. It doesn't really stabilize as well. So here's the solutions to those. So chain 2, what we did was we just cut out the first whatever, the burn-in, and so now it looks pretty good. Second one here is to solve this, increase the sample size. So this was like, what, 10 to the 5th, and so that was only like this much, and it increased it a lot more, and it now looks pretty good here. Here are some examples of chains we see here with these with the burn-in attached. Initially they're pretty off, but these kind of converge pretty well here. These mix very well here. These ones haven't really mixed. They're all still kind of bounced around. They're not agreeing very well on a common value, so these might need to be run out longer. Okay, here, so let's look at diagnostics now. We've already kind of seen them, but let's dig more into how we diagnose them. So there's those trace plots, what we've seen already. There's also autocorrelation lag plots, and of course our probability density functions and intervals. So this is what typical diagnostics looks like in SAS. So these are our trace plots, these are our autocorrelation plots, and these are our probability density functions. And so what's interesting here is obviously we look here initially to make sure it looks pretty even. There's not it's around the normal value. For our correlation, it should drop off as leg goes up. If it continues to have autocorrelation as it goes higher, that's a problem, and we might need to deal with it. And then probability distribution function kind of gives us information about our parameter. So if we're looking at this beta, looks like its probability is about negative 0.25, and it tapers off. And if you look here, it's pretty interesting, 0.025, and you see here, that's the same average sort of value that this is converging towards. So if you can imagine, like, these are a bunch of like probability density functions at each level here, and you combine them all together, you'll get, voila, that. So what does this look like in R? Pretty similar. It doesn't automatically, most outcomes we see don't do the autocorrelation, but it'll still have the trace plots and the density. And again, you can see here, so the average for A looks like it's like 4.85, and again, that's what this is showing. This one's much smaller, it's 0.1045 or something. And then you can see the number of iterations are kind of generally shown here, and some other information. Okay, so with that, we've kind of gotten through the background information here. That gives us enough tools to look at examples. If you want to take a moment here to take the first assessment, it's found in the link here. The link is also found in the description below. Let's talk about our example setup. We'll be just using R and SAS today. For R, we'll be using packet RJAGs. We'll look at the probability of a single value, simple and multiple linear regression, and Poisson regression. For SAS, we'll be using proc Mcmc. We'll just be using simple linear regression, mixed effects model, and logistic regression. More information on these packages and procedures can be found in these resources here that we found at the end as well. All right, and the R code and SAS code for these examples will be found available at these locations here. So let's get started with our step-by-step example. So just talking about RJAGs in R, it is a package that helps define models using this bugs language in a separate file. It reads it, updates it, and it extracts it. But for our purposes here, this is the useful steps that we'll be covering. We'll view priors, we'll view data, we'll define model, compile model, and simulate model. Those are kind of from here. That's the actual meat of it, and then plot results. So these things are sort of the visualization and results. So let's get going here. Let's look at the probability of a single value. This is a very Bayesian sort of thing to do. What are the chances of winning a vote? So let's view our prior. So we think we fall under 50% of the votes. We're not quite there. So we're going to create a ggplot. And we're going to set it up with a beta distribution, and we're going to have a shape of 45 and 55, which will kind of bring us just below that 5.0. It might give us 50% or more, but it's more likely to be slightly lower. And then now let's view data. It's not really what we're going to do here because it's very simple. That we did a small poll and found that 6 out of 10 people would vote for you. So this is our prior. This is our data. So let's define our model now. So this is how the setup goes. You have to have this hashtag define model, and then, that's just reference text. So vote model is going to be this string model. We have to have a likelihood model. So we're going to model X, so that variable, our proportion of probability of winning, as a binomial with P and N, and then those P and, so N is going to be our number we'll fill in later, but then our P is our prior model. Our probability is going to be from a beta distribution. with a shape parameter a and b. So how we compile this model is we're going to use this something called vote jags, and we'll use this function jags model, text connected. We'll connect to our vote model text, and then we'll add our data. So our data for our beta distribution is going to be 45, 55. That's our prior. And then that small data model, well, we had 6 out of 10. And then there's this initiation. This is, you can kind of just fill this out. This won't really change as we go through, including the seed. The seed, essentially, if you set this seed, it'll replicate the results. So if you set this to 100, it should give you the same results I'm doing here. If you don't set a seed, it'll have slightly different things because it's simulating each time. And then we'll simulate to posterior. We'll create an object called vote sim. We'll use COTA samples, use our model vote jag. So this is going down here now. Variable names, so just our probability, and then we'll set the iterations to 10,000. That's pretty standard. And then we'll plot our results. We'll look at our summary and our plot. So this is what the summary gives us. So summary gives us some information here, but really what it gives, it's helpful, it gives them our mean. So as we suspected, we're a little bit below 0.5, and these are quantiles. But then these are the real meat, the plot. So the trace plot looks good, and then this gives us our probability density function. So yeah, mean is around 4.5. We can see that really we hope to win 50% or more. It's definitely within bounds, but there's quite a bit of uncertainty here. And so what we saw here is we had our prior, a pretty strong prior and a relatively weak data. So the prior was the stronger determinant of our posterior. So what if we want to update this? Maybe we should use updated data. So what I'm going to do is create a new prior here, given so this information is coming from the output of our previous one. We had a mean of 0.46 standard deviation. So this is our new prior, gives us more information, and we're going to plug that back in, just plugging these in instead of having variables, plugging them in directly. And then with that, we'll have some updated data. We took a larger poll and found that 688 of 1,000 voted for me. So you're going to add that into the data list. You can see here we don't need that n and p because we already defined that earlier, but we do our x and our n, which we come from this poll. Plug that in here, run that again, and now what we get here is we get a higher mean, 0.68. So we had a much stronger data, gives us much more information than our prior, so that's driving our posterior. Indeed, what it looks like here is we're much more likely to get more than 50% of the vote than before. So it looks like our voting is in good order. And this is looking back at the previous one. We see here what this was much, much lower. So, and then obviously as more polls in, we could keep doing this to really drill down into our likelihoods of what our vote would be. Okay, so now let's take some simple linear regression going on here. Can weight be modeled as a function of height? So let's view some priors here. So the three priors here, we're going to have an intercept, a slope, and a standard deviation, because of course you know that with an equation of a line trying to predict linear progression, we're going to have the slope, the intercept, and then how variable it is. So we're going to bring these all from normal distributions, except for S, which is just going to be a uniform distribution. And so we're just going to create some mock data, pulling 10,000 samples from a normal distribution for A, B, and S, or S is uniform. We're going to put them in a data frame called samples. Here's the head here. And then here we'll do 3 GG plots. So this is our A, so our intercept, our slope, and our standard deviation. You see here that the intercept is pretty broad. It could be anywhere from -500 to 500. Our slope is much more constrained. It's above 1, or it's around 1, but it could be as low as 0 or high as 2. And then uniform is pretty broad. You see here that this isn't like that straight line that we kind of see here, because this is simulated data drawn rather than theoretical modeling. Okay, so let's view our data. So we're going to be taken from this BD dimension. So we have weight as a y variable, and then our height as an x variable. And it looks like there is a relationship as height goes up, weight goes up. So let's see how that bears out. So we'll define the model. So the likelihood model is going to be a little bit different. With regression, it's y for each I iteration for I in length y. And then we're going to have a normal distribution with mi, and then our standard deviation. And then m is going to be this function like intercept times slope and then times x. Our prior models, which we already looked at here, we're going to define them here. Then when we go to compile our model, again, we'll create something called weight JEGs now, which will use our weight model. We'll need to add our data. So we'll have our x and our y variable, which are those height and weight dimensions from our BDIMS data set. This is all going to be the same. We'll simulate. Again, the main difference here is obviously we have weight sim and weight JEGs rather than the other things like our vote sim and vote JEGs. And then we'll also need to include more variable names, A, B, and S, rather than just P. We'll do a summary and a plot. So summary here, we get the estimates for the different values, quantiles, but then here's the outcome here. And we can see here that right away A and B kind of seem to have some correlation that we might want to, if we were doing this longer, we might want to run this out more. But for now, let's just call it okay, and S looks pretty good. So it looks like our slope B is somewhere around 1, where our intercept is somewhere around like -100. So what if we want to update it and increase our iterations? We can just change that here, do the same sort of thing. Pretty similar outcome, but these traces A and B are starting to look a little better. And then the densities, still pretty broad, but I think that's what we can work with here. So what if we want more chains though? Well, we can actually, by default, I think it's just 1, but if we want to actually add it ourselves, we can add a comma and then just add whatever number of chains we want. Do this again. And then we're going to get same sort of outcome, but then here are our plots. I did this, instead of plotting everything, I just did trace plot just to get these trace plots. We can see here, it's sort of hard to see. There's actually different colors. You just see the blue because that's on top, but what that means is all the chains actually mix pretty well together because you can't, they're all kind of tracking the same way. Again, A and B, since we drop back down to 10,000, aren't the greatest, but at least the chains are converging. So what this kind of tells us is, while there seems to be a good relation between height and weight, there's a lot of uncertainty that we saw in it. And again, we can some plot results. So what we're going to do here is your ggplot, and that was our raw data, and then we're going to add lines. So I'm taking this information. This was intercept and slope. This was from the results of our simulation, and that's going to be our best fit line, and then our 95% sort of intervals are also taken from there, and those are the dotted lines. So this is the best fit. That, yeah, there's a pretty like 1-to-1 relationship. As height goes up 1, weight goes up 1. And, there's a fair degree of uncertainty, though. Okay, let's change tack a bit and beef up our regression into multiple regression. Can we model volume by temperature and weekday? So we're going to have to view a few more priors here. So what we're going to need here is a weekday is going to be a categorical. So we're going to need an A, which is weekend intercept, B, a contrast between weekday and weekend intercepts, C, a common slope, and an S, residual standard deviation. We're having pretty general priors here. So these all are going to be from a normal distribution, and again, our standard deviation is going to be from a uniform. Created them to a data frame called samples, do a head of this. That's what it's kind of getting simulated as. And these all look pretty normal, this normal distribution, and then our uniform distribution. All right, let's view our data. We're going to go from library mosaic. This is our rail trail. And then let's take a look at the head. There's a lot of this information. We have high temperature that we want to use, weekday, and then we're trying to model volume. So we're going to do some just formatting to get it in the right format, and then run a ggplot just to kind of show what we're trying to get at here. So we're trying to model volume as high temperature and weekday, and it looks like as temperature increases, so does volume, and then that it looks like weekend, so that's the false weekday, might have more volume than weekend. In fact, they might have different slopes, though we're not going to change the slopes, just the intercepts for this. Okay, we're going to define the model. So this is going to be that regression style definition. We have y across iterations as a normal distribution, and then this is our equation here, a, b, and c, with x and z that will come from the data. So these are our prime models. We already kind of looked at that, but this is a little trickier. So a is just a normal distribution. B, so if it's a, because our weekday is a categorical variable, essentially if it's set on 1, that's going to be 0, but if it's 2, it's going to have a normal distribution because there's a difference between weekday and weekend, we think. And then C and S are pretty standard here. Compile the model. This will all look pretty the same. Just switching out rail jags and rail model for the previous model. And then here we're going to need to, our y and our x and our z are going to be our volume, weekday, and rail trail. We can see here that rail trail is our x, and that's a categorical. So in our model here, you can see here that b times x, and then z is our rail trail high temperature, so that's going to be over here. And then if we simulate posterior, again, the only change is sim and jags is going to be rail now. We'll make sure all our variable names, of course, summary plot, and then we're going to look at create a new data frame here. So this is what the outcome looks like here. We have means for all these parameters, quantiles. This is what comes up here. So density of A looks like it'd be about 0. Density of B, that's flat. Density of B2 is around -50. C is around 4 or 5, and then S is here. So what does that mean here? So what we're going to do is run another ggplot here, and then add from, I reset the data so we can pull out information from our rail simulations. So we can get our A, our C, our A, our B2, and again C. So essentially we can get that information. C, of course, was our slope. Our intercept was A and B2. And what we see here is, yeah, it looks like for every 1 degree in high temperature, volume of visitor goes up by about 5. And there's about 50 more people per degree on weekends. So, okay, well, now let's take a look at Poisson regression, because same data, can we predict volume, but now this time as a count variable by temperature, and then later weekday. So again, we're going to have A as our weekend intercept, B as our contrast, C as our common slope, and S as residual. This really isn't going to change at all, so we'll just blow through this, same sort of thing. But then viewing our data, again, we'll start with the simpler model. We just have volume and high temperature as Poisson. But then later, of course, we're going to be looking back at volume, temperature, and weekday. So what this looks like for the simpler model, we have a likelihood model here, but now this is a little bit different because we have Poisson. So we're going to have this log transformation here, A, B, and X. Prior model is A and B. We'll compile our model using our X and our Y and our X from the rail data set. Simulate it, make sure we're A, B, so these things are all changing. We'll plot, summary, and then set these in as data frame to, I think, be able to plot it in a ggplot later. So this is the outcome. We have our means for A and B. Traces, let's look okay. Looks like, again, we can match this up here. It's about 4.85, 8.6. That's the same thing it's giving us here. And this is 0.015 about. That's the sort of most likely area, but then of course it spreads out here. And if we again look at things like quantiles, you can kind of give us a spread that's sort of down here, and this is sort of up here. So that's, you can see the plot, the information of the plots is also, these are different ways of giving the same sort of information. Okay, so let's plot results here, and now again we're going to take from this Poisson Chains data frame we created. We're going to input things like our A and our B, but we're going to have to back transform it because we had this log transformation. But if we do all this here, this is what we get. And we can see here that, yeah, indeed, as high temperature goes up, volume goes up. But since it's a Poisson distribution, which has it's limited, it can't go below 0. We have sort of this curved plot. So if we really actually extended this out, so let's really just go for it. If we could theoretically extend this out as far as we want it, something at some point, you see it'll never actually go below 0. It'll just approach 0. So that's kind of a more realistic information about this. Like, we'll never expect volume can't be negative, volume of people, so the number of people coming in. So this is maybe a little more realistic. Okay, so let's update this and include our weekday. So we're going to have to add this variable here in our likelihood model, add our B's back, like we saw before with the multiple regression. We'll compile the model. Main thing here is we're going to add the Z. Plot results is going to be more complicated. Again, we're going to have to back transform some of these things. We're going to have our C's, our A's, and then our B2. And these are the outcomes here, A, B, and C. I didn't show you the trace plots, but here we go here. Again, we see the same sort of information, though now the thing is curved. As temp goes up, volume goes up, and weekends, shown in red here, are higher than weekdays. So you see here that these lines aren't quite the same. You can see there might be a spreading out here, so that there might be a bigger difference at higher temperature. It looks like there's a bigger temperature, yeah, at higher temperature than lower temperature between the two. On the weekends, if it's really hot, nice out, even more people, it's stronger a relationship. Okay, so that was R. Let's switch around and see this played out in SAS. So the procedure we'll use is Mcmc, and this is how following statement would have. We'll have a proc, array. It doesn't need all of these, but these are the typical statements. This is what our steps are going to do here. Pretty similar. We're going to get data, view priors, and then run analysis. So we'll run this proc Mcmc and then plot results. So kind of similar to what we did with R, though the analysis is a little more condensed because it's just one procedure. So let's start with simple regression. Same sort of thing, different data set, but same question. Can we model weight as a function of height? So we're going to get data. There's this data called class that we're going to create here. There are different students. We have height shown in this column here and weight shown in this column here. We'll plot it, and this is what it looks like, height and weight. So let's view our priors here. So we're going to use the thing with proc Mcmc, you actually can use it to view priors. So what you do is you just, earlier I just created a data set called data A. It's just empty. And then you just want to do that. You can name it whatever you want, A, X, wherever. But then you can call it here, called data A, and then stats none, diagonal in. This is the number of iterations. And then you can create your outputs. So you have plots, model. Model is going to be general 0. So you're not going to have a model, but then these are your parameters and priors. So we're going to have we're going to have 2 betas, so beta 0 and beta 1. That'll follow a normal distribution. And then a sigma is going to be an I gamma. It's going to be very sharp here. This is a little bit different setup of priors than R does, but this is what Mcmc sort of like defaults to, a very broad priors, and then an inverse gamma for some reason for the sigma squared. Of course, you could set up whatever you want here, but I'm just following what the examples that SAS has set up. Okay, so we're going to run analysis. Now for real, we're going to run proc Mcmc, so the data is going to be needed for class. We're going to run this a little more. We can thin it, set a seed, so if you use this seed, this should replicate these results. If not, it'll be slightly different because it's simulated. Here's our parameters again. So our beta 1. So I think these are just sort of filler things, just include them as they are. So our first prior is you can actually combine this, so both the beta 0 and beta 1 has a normal distribution between a 0 and a huge variance. You could also separate this out. You could like have 3 lines. So you could have, prior and then beta 1, with this, and then you could have beta 0 just right here, or you can combine it if it's the same thing. So that's what we did here. And prior sigma had an inverse gamma with 2 shape parameters. And then our model is going to be down here, but first we need to find mu that's going to go in the model. So it's going to be beta plus beta 1 times height. So that here it's confusing because their beta doesn't mean a beta distribution. That means this is essentially what you might say is b and then this m in like y equals mx plus b, where this is the intercept and this is the slope. Now I think you can call it whatever you want, but this is how it's just set up, so I'm just using the terminology that it's here. Then in our model, we're going to model weight as a function of a normal distribution with our mu here, and then variance of sigma squared. So this is the outcome, so posterior summaries and intervals. So the main take-home point here, let's switch some colors here, brighten up a bit. So we get estimates for our parameters. So our slope is -142. That's our intercept. Our slope is almost 4, and then our variance is 137. And here are the diagnostic plots. We can see all the trace plots looking good, autocorrelation plots looking good, and this again gives us our probability density functions. Should be very similar. You can essentially reconstruct this using the mean and these intervals. Like for example, our beta 0, again that's our intercept. This is about like 142 here, and we can see that that's true. And then the top and bottom, so 210, so 95%, so that's going to be somewhere around here. So 95% of the probability is going to be between these two, and then -77. So yeah, that's about here, and that's our 95% probability density interval. Diagnostics for B1, very similar. This is almost 4. You can see, yep, this is almost 4, etc. So what does that mean for our plotted result? Well, we're going to use proc SGplot, use our data class, and I'm going to enter that outcome data for the slope and intercept manually. So we're going to first of all do a scatter plot of height and weight, and then to create this line, we're going to use line parameter. So x is 0, and then this is our intercept, -142, and then the slope is 389. And then change some things with the attributes. to get it set up. I also had to reformat the axis so it still fit within what we wanted here. Otherwise, it zoomed it out because of the intercept. Okay, let's change gears and do a mixed effects model. Can we predict height by gender while blocking for family? So this is going to be our y, I'm going to say x1 and x2, so that though this is going to be a random effect and this is going to be a fixed effect. So to get data, we're going to create a data called heights. So it's going to have family, G is gender, and then height. So families 1 through I think 4, gender female or male, and then height is here. And then we're going to reformat some of this stuff to get gender G into gender, just to clean up a little bit. And what we get here is family, height, gender. Great. There we go here. Let's switch colors again and move on. So we want to view our priors again. We just use this empty data set, and we're going to set up here. And what's going to happen is we're going to have our typical B0 and B1 slope intercept, but then we're going to have an array of gammas, which are going to be very sharp. 1, 2, 3, 4, and then our standard deviation, and then our standard deviation based on gender. And so these gammas are for each of the four families. So we'll actually run the analysis. Pretty similar here, though. Now we have our actual data we called input. We can do things like thin, have the number of iterations. Again, the seed, this needs to be this to get the same output. If you want to do a different seed, that's fine. It would just be slightly different. And we're going to monitor B0 and B1. What this sets up is, because we don't actually care about family, we just want to block for it, or like treat it as a random effect, we're just going to get the outcome for these ones. So we're going to set up parameters. This is our model here, B0 plus 0, 1 times gender, and then plus gamma, and then this is the family. So each family has its own gamma, and then the model that's coming in here that takes the mu is height as a function of normal distribution of mu. So we're not going to really plot results here because this is more complicated. We're just going to look at the summaries, intervals, etc. So here are two parameters. It looks like our intercept is 64 and our slope is -3. And here's some diagnostics. These look pretty good here. Again, this is replicating what we see here. This is about 64. This is about -3, though you can see here that there's a pretty large interval. And this encompasses 1, so the slope could very, very likely be not exist. So with that, let's change tack and look at logistic regression. Can beetle death, which is a binary variable, yes or no, be predicted by contaminant? We'll get data. We'll create our own beetle data here. There's going to be a variable n, x, or y, and x. So no, whether it died, yes or no, and then the contaminant x. So the level of contaminant. So what this looks like here. So for the first observation, out of 6 beetles, none died at this level. Though if we go over, here, there is a total of 9 beetles, 6 didn't die, 3 did die. So that's what's kind of going here. So we can look, again, view priors here. This time we just need a alpha and a beta prior. And what this looks like here. Alpha, and these are around 0 from a normal distribution. So how this is going to be set up in Mcmc. A variety of things here. The main thing we want to look at here is we have our priors, alpha, beta, our p. Our probability of death is a logistic model using alpha and beta times x. The model is be from a binomial with n and p. So again, we're not going to plot results, but what we get from here is our alpha and our beta. And alpha from both here and here is definitely negative, centered around a mean of -11. Well, beta is small but positive around 0.03. So what this means is that for our example is because beta, especially because beta is positive, that as the contaminant X increases, so does the probability of death. And now it'd be better normally to run more analyses, like especially with this sort of like the survival data, is like look at the 50% lethality dose or like do other things like that. But for our purposes here, we just wanted to run the Bayesian analysis. That'd be sort of downstream things that are outside of the scope of this example. Anyways, with that, we've ratcheted through R and SAS, so you can relax and unwind and take a second assessment found here. So let's make sure we've got all our ducks in a row with some caveats and concerns. Now, as you can kind of see here, and we breezed through a few of the examples, modeling priors and parameters can get tricky. So make sure you easy do it. Start simple. Maybe start with a simpler model and build from there. Like for example, with the Poisson regression, we ended up doing both numeric and categorical, but we started with sort of like the simpler regression before building onto it later. So that's a good rule to try. And again, you don't often need to go through Bayesian complexity for simple things. Bayesian analysis is very useful, but if you have pretty tight data that doesn't have a lot of uncertainty, you don't really need to know how uncertain your data is. You might not want to go through all this for something like that. And again, there's more than one ways to Bayesian a cat. There's a lot of ways you can run Bayesian analysis, especially in R. We saw our JAGs here. We used Bayes factor earlier. There's all sorts of Bayes packages. I think there's at least 100. So you can find a way that works best for you. And then, of course, we didn't set all the sort of parameters we wanted to. We didn't really do anything with thinning, seed, or tuning loops. There's a lot of ways you can treat both like the Mcmc and SAS and the RJAGs. And again, it's not always easy to visualize the results. And you can follow some of the references I have at the end that will let you do so. And that's very helpful in making sure you're understanding what your output is and presenting it to people as your conclusions. And sure, make sure you're working hard to interpret outcomes. This Bayesian analysis is initially pretty overwhelming, and some of the variables maybe aren't so clear. So really work to understand what's coming out, so you're having proper interpretations. And again, there are very strong opinions with the underlying philosophy, especially Bayesian analysis, that really you should, and you can follow this sort of link here, or sorry, this reference here that's found at the end that goes into more why Bayesian analysis should maybe be preferred. But again, I don't really fall into that sort of camp. I think both frequentist and Bayesian analysis have their place, but just know that that's out there, and there are arguments for either side. All right, let's take some real-world examples here, flush out our minds, see what other people have worked hard to produce. So this is risk profiling in soil-transmitted Helminth infection. So background on soil biology, might as well take a look here. They transited with what's called a Bayesian geostatistical framework. So our old friend Markov Chain Monte Carlo comes up here. And they looked at these different infections of Helminths. These are parasites, hookworm, and these A. lumbricoides, and then G. trichinella. I kind of split this out just to see. They looked at a bunch of variables and found which ones were important for the different parasites, so things like spatial range for the hookworm. Spatial range came out, but also soil moisture, soil acidity. Hookworm had rural urban was important. Rainfall for T. Tricharia, and also spatial range, of course, variance. So, just a little bit there. Moving on, let's look at Bayesian hierarchical change point methods for modeling tumor growth profiles. So I currently work in biomedical, so cancer is a daily part of a lot of my research. So they use hierarchical change point methods to model tumor volumes. So this is kind of cool here because they actually gave you the code. So you can see here, very sort of similar but much more complicated to what we worked on. These are the sort of the RJEGs setup. You have the likelihood, pretty complicated mu there, prior, pretty extensive priors, but that's kind of cool to kind of see it in action. And then they got these change post models of days, and then these volumes of these tumors. You can see that. So these are modeled a little bit differently than just a simple linear relationship. Okay, so here is a bit of a comparison between Bayesian frequency model selections. So this is kind of cool because they use a bunch of model fit indices and then model selection for Bayesian, and then looked at all sorts of graphs of essentially all these different methods and how well things fit. A lot of information here. This is kind of cool to kind of see all of it in action. All right, so some summary and conclusion here. As we've hit you over the head several times now, Bayesian analysis takes in prior beliefs and evidence to generate posterior beliefs. That's what's going on here. The detailed method of running analysis is defining priors and parameters to construct a likelihood model, and then standard inference and diagnostic output, things like trace plots, R correlation leg plots, and probability density functions, and things that complicate quickly. So I've dived as deep as I could go here, but there are great further depths to explore, and I have some great resources here. So with that, here's our references, just floored by the inundation of blue hyperlinks awash in it all, so you can definitely follow them here, and there should be links to the description below so you can follow them more easily. And finally, we've come to the end of our time here. Some acknowledgements. As always, the DaCCoTA that I'm a part of is supported by the NIH, so please cite us if you found this important, useful, or otherwise engaging. Thank you.